Hello everybody, I'm Josh Whelan. I am a mechanical engineering design intern and I did a project on the 7 degree of freedom robot design. As a part of my project, I had 3 stages to my design: research, design, and then test. So first of all, I started with research. The first thing was determining what degrees of freedom are. So I knew a lot coming from university and some courses that I'd already done before, but when I was a bit daunted by the whole fact that there was a 7th degree of freedom, so I had to understand what that actually meant. In robotics, a 7th degree of freedom is an extra motor on it. So each on my design here is 1 motor. So this one is 4 degrees of freedom because it only has 4 motors. Whereas a 7 degree of freedom robot would have 7 motors on it. In our object world, however, we only have 6 degrees of freedom. And that means that a robot with 6 degrees of freedom can get to any point at any angle that it possibly wants. But we can have extra degrees of freedom, and that's where my design comes in. The 7th degree of freedom allows for extra movement around certain objects, as you can see in this video here. As you can see, the 6th degree of freedom robot is on the left here, and then this is the 7th degree of freedom robot. Almost exactly the same, except it has that extra axis of rotation that you can see there. Now, what's important about the 7th degree of freedom robot and the difference between it and the 6th degree of freedom robot is that a 6th degree of freedom robot can get to any point in space as long as it's not blocked by an object, which can be seen here with that pillar right in the middle. As you can see, the 6th degree of freedom robot couldn't quite get around the pillar there, whereas the 7th degree of freedom robot can get all the way around and, as it's a welding robot, can weld all the way around the edge of the platform there. As you can see, it could get all the way around and a little bit more. And that's what the 7th degree of freedom helps with. The problem with that is that it adds an extra degree of freedom, adds singularities. The problem with singularities is that on a 6th degree of freedom robot and other degree of freedom robots from 5 up, it causes problems when you want to do motion in one direction. Once it gets close to that singularity, the motors will have to slow down to their maximum speed. If we could just go to infinite speed, it could just go straight across at a constant rate. But as soon as it gets to that midpoint, the motors will have to be tapped out and the motion will slow to a near stop, if not a stop, and then keep going, which can be seen in this video here. There are also FEA singularities, which I'll get to in the future later in this presentation. So the first singularity for robots is wrist singularities. As you can see there, the end effector is in position, it is not moving, whereas 2 motors are actually moving in opposite directions. And as you can see there, there's a perfect situation of it. It's moving across that x-axis, but when it reaches the middle, it stops moving as quickly as possible. Elbow singularity is pretty rare. It's only when you fully extend your arm, which is almost never the case. The last one is shoulder singularity. As you can see, the whole shoulder is moving around, but once again, the end effector is not moving in place. And as seen by this, similar to the wrist singularity, it moves across, and once it reaches the middle, it starts to slow down and even stop before progressing towards the other end. Okay, the next part of my project was design. Now, after my first design, and even second and third designs, I went back and did more research on concepts that I could use and different things. So I did go back and forth between the 3 stages, but design was the next section. So this is my first design. It's based off of my friend's Mel's design, which she did here already. It's a symmetrical design, which means that even though the motor only faces out one way, there's an arm on the other side, as you can see on the top left here. There were problems with this design though, as I made it with cuts, so that way it can actually be put on the motor. They went through the screw holes, meaning that those screw holes that were cut through are completely useless and do not hold the the frame in place around the motor. The other problem with the symmetrical design was on the back end. I just had a ball bearing attached to the little fork, as you can see on the top left, to a tiny little nub on the back. Basically, that would do nothing. Either it would take no force or it would take way too much force and break. So I need to make changes to that and rectify them. That's where this design comes in. This is my second and final design, which is an asymmetric design. As you can see, only one half of the only this side of the motor actually extends upwards. There's nothing on the back end. This means I had to reinforce it a little bit more to deal with the forces and to deal with the stress of having the motor on the edge right here. So I also added smaller details to the design of this 7 degree of freedom robot. Some of the things were the wiring holes, which you can see here, and the indents on the bottom of the motors, as the motor actually has a little bit of extra space underneath, so it's not completely flat. So I had to make rectify that, and it fixed pretty much every other issue in the previous design. Finally, I made up to a shell design. The shell is just to make it look pretty from the outside so that people, when operating it, don't see the disgusting wiring and other things on the inside. So there were two ways of going about this when it comes to attaching the shell to the frame. The first one that I consider were clips, very simple to use. Anybody can use them without any equipment. The problem is that the two ways that I came up with this was either like you find on battery holders, which just stick in and then you push them and they come out. You can't easily put them on this shell design, as we want it to fully encase on both sides, meaning that we could easily get it on or easily get off and not stay in place, which is a problem because we want it to go both ways. The other idea for the clip was similar to one that I found on my bike radar at home, which is where you twist it, you put it in place, you twist it 90 degrees and it locks into place. However, as you can see by this diagram here, it wouldn't perfectly align, as it would go through the frame, as I didn't want it to be too bulky. So either I don't use it and it just goes through it, or I make it larger and it's a bit bulky, and that's not what I wanted to do. So the design that I went with was to use screws. So as you can see, there are bits that are protruding out and there's holes on the outside of the shell. So you could use screws to go through there. There's two ways of doing that. We can use self-tapping screws, which would actually thread the hole for me. Or I could use pre-threaded inserts, which I could insert into the holes that you can see there, and then you just screw a normal screw into that position. Final section of my project was testing. Testing was also important with my design. As you can see, as I mentioned before, there was the asymmetric design, which could cause problems with the weight going on only one arm. So that's where FEA analysis comes in, finite element analysis. What we tested for was stress, deflection, and strain. So stress is important. I chose a very mid-range steel, sort of to the lower end of ultimate strength, which was at around 350 megapascals. On the top left here, we have my von Mises stress FEA. And as you can see, there's a tiny little red dot where the two cylindrical sections meet. That's where we most likely expect those stresses to be at its highest. And as you can see on the top left, it actually was below the ultimate strength of the steel that I chose. The other important part of this was that I used a safety factor. Safety factors are important because they make sure that even if we double the worst possible outcome for a certain thing to happen, then we don't have to worry about it. It's made to be very safe. So for structural designs such as this one, I just use 2. If we were to do medical designs and stuff like that, we'd actually use 4. But because this is just fully structural, we only had to use 2. So we can also see it on the full design, which I put together there. It is much lower than the ultimate yield strength. And on the right here are the deflections with the maximum deflection of the full thing, with all the torques going in the same direction and all the forces applying in the same direction. It only went about 2 millimeters, which is not much for a more than 1 meter long robot arm. So here's the design of the tests that I printed out. So my first print was only of 2 degrees of freedoms, because those are the only motors that I could find. The whole point of the test was to check whether my designs were correct and they fitted, and also to check that the engineering drawings provided by the manufacturer were correct, which I found out to be not true. The first design worked very well apart from the wiring positions. So you can see the holes there on the left. They were actually about 2 millimeters out according to the engineering drawings. So I had to rectify that, which I did in the second print, which I got more motors and made it a 4 degree of freedom robot. I also had some problems with screw holes being a bit too small or being the wrong size, so I increased them for this one. My third print, as you can see here, I also added in indents, so that way when I screw in to certain sections of the motor which are very deep in their thread, I could put them in without issue. And the same with this motor here, as it is the same size as the motor above. It's completely flat, so I really needed the indent and screws there because there was probably about 1 mil in between, and unfortunately the screws weren't that small. Finally, I also printed out a shell. Unfortunately, I wasn't able to put it all together properly with the screws, whether that be self-tapping or the inserts as mentioned before. But this is sort of what it would look like with my 4 degree of freedom design. It's all attached, and I also had a base plate, which you can see also here, attached to it, which in the full diagram would actually have the full robot arm would actually be incorporated into the first motor shell, would be right on the bottom, and that would be able to attach to that base plate or indeed convergences. So any additions and improvements that I'd make, I would obviously want to build the entire arm with the 3 extra motors, which would be below this one. I would want to test any simple movement to make sure that that it can move freely in any position that would be required. I would properly attach the shell, whether that be with self-tapping screws or with those inserts, and I would use better software for FEA as I only had access to SolidWorks. Thank you very much.